Hi, my name is Molly Darby, and I will be doing this presentation on Arima supply chain modeling. That may just sound like a bunch of words that you don't know at the moment, but hopefully by the end of this presentation, you'll have a better understanding. So let's get to it. The first thing I believe we should cover is what is a supply chain? Many of you may know what it is, but then again, some of you may not. So let's just go over some of the basics. In short, a supply chain is the system by which products move from supplier into the hands of the consumer. Sometimes there's waste that ends up coming back into the system as an input, but basically it's just the system that moves products from the beginning to the end, from raw to finished. So typically a supply chain is made up of the supplier, that's the person who has the raw goods, such as cotton or vegetables. Then you move to the manufacturer, who then manufactures a specific product out of those raw goods. That product is then distributed by the distributor, which ends up at a retailer. That could be a grocery store, it could be a storefront, and that's where the consumer purchases it. A couple concepts that are going to be very important throughout this presentation that I'd like to highlight now are lead time and bullwhip effect. Lead time is a pretty basic concept. It's the idea of when you order something, there's a time delay between when you order it and when it arrives. So making sure that you're ordering things at the right time is crucial because you want it there at a certain time. The bullwhip effect is a little more complicated, but basically it's when variations in demand cause an effect upstream in the supply chain. For instance, with the romaine recall, there were limited supplies to romaine. Therefore, companies were ordering more of iceberg lettuce and other types of lettuce. This increase in demand in the different types of lettuce caused a problem further up in the supply chain because they weren't able to meet that demand. This is magnified further upstream because if you think about it, it may just be one or two restaurants ordering more iceberg on an individual level, but when that goes back upstream, the supplier is majorly impacted by hundreds of thousands of restaurants at the same time. Now, I think we're ready to talk about the ARIMA part of this presentation. So let's discuss what is an ARIMA and how does it relate to all this economic supply chain stuff. ARIMA stands for Autoregressive Integrated Moving Average. Now that still may just seem like a big jumble of words to you, but basically it's a way of dealing with time data so that you can forecast the future and make predictions based on what happened in the past. This is helpful for modeling supply chains because as you can see from the concepts of lead time and bullwhip effect, time is very important. Optimizing ordering is also another benefit of using ARIMA models to predict because the goal is you want to order what you need so that your customer is able to purchase it, but you also don't want to order more than you need so you have a surplus inventory that just costs you more money. Now that we've gone over the concepts of ARIMA and supply chains, it's time to get into the formulas. Now, these formulas may be a little complex if you don't have a math background, but I'll try and make them as simple as possible. This slide includes formulas for the demand model. The first formula is a typical ARIMA model formula. ZT represents your prediction at time t, while mu is the mean of the time series or the variable of interest. Now, these fees and thetas are based on fitting the model and finding the coefficients of order P and Q that fit the data best. The best way to do this is to use AutoArima in R or some other type of software, and it will optimize your prediction while minimizing the errors. The next formula is for backshift notation. This is really just another way of writing the formula so that it doesn't look as messy. So the B will represent ZT minus a certain number. The formula beneath is for a non-stationary time series. That just means that the time series is not independent of time, which you want it to be. So what you do is you take a difference. The next formulas I recommend pausing the video and taking a look at because really it's just a different way of rearranging the variables and rewriting them, but it's no new material. The formulas on this slide are for the supply chain model. The first formula represents a relationship between the inventory for the period before the order placed, and that's equivalent to the ending inventory for period T. Beneath is a formula that expands on the order placement. OT is the order placed at the end of period T, whereas big T is the target ending inventory. You want to have a little bit of cushion there. It's considered a safety stock. The main difference here is Z hat T instead of regular ZT. The hat signifies that it's a forecast, that it's an approximation. The other important thing about this formula is you can see that the actual inventory is going to vary from the target based on forecasting errors. So the more errors that you make in your forecasts and your predictions, the more your inventory will deviate from your target. Theorem 1 has an important result, and that's that it gives you a measure of the bullwhip effect on the inventory. Another important thing about Theorem 1 is that it gives you an idea of the orders that you're going to use for your Arima model of inventory, which is 0, 0, and the lead time -1. This formula can be applied to different stages of the supply chain because if the demand is a certain number for one part of the supply chain, then it can be deduced that it's going to be the same for the next level up in the supply chain. Therefore, these formulas can be used recursively to find your values for different parts of the supply chain. Another important part of this is the K value. K represents a ratio of the standard deviation of the inventory to the standard error of the forecast, and this is what allows us to measure the bullwhip effect on the inventory. Theorem 2 is regarding the time series of orders with an Arima of values P, D, and Q sub O. QO changes, however, P and D are the same orders as from the demand model that was presented earlier. An important thing about this theorem is that it gives us a measure of the bullwhip effect on orders, which is a ratio, again, just like the other one. However, this is a ratio of the standard error of orders to that of demand. I recommend you pause the video and take a look at the changing value and how the noise series is affected. Now let's discuss some of the conclusions of the theorems and the formulas that I've laid out. Basically, we've decided that the bullwhip effect is large or larger when lead time is long and autocorrelation of demand is high. That makes sense because if you have a long lead time, a lot can change during that time. Demand is given more time to fluctuate. So when you're receiving less product more frequently, it's easier to optimize. Also, the number of stages doesn't matter so much as the sum of all the lead times, which kind of goes along with what we just talked about. Minimizing your lead times is going to minimize your fluctuation. Therefore, the number of stages doesn't really matter. It just matters how long it took to get the product from stage 1 to stage 2. Another important result is that the bullwhip effect cannot be eliminated completely, no matter how perfect the conditions. One proposed solution to the bullwhip effect is to improve communication and have point of sale data sharing. This can be kind of redundant, sharing your data, because based on the orders you're placing, it can be deduced what the demand is. It's more important to communicate future changes, such as having a promotion or having a sale. If you can communicate things like that ahead of time, that could make an effect on the bullwhip effect, but not simply sharing your demand data. Thank you for joining me for this video, and if you'd like more information, there is a citation for the paper that this information came from on the next slide. It also provides proofs of a lot of this math, so if you're interested in seeing the nitty-gritty of everything, please feel free to look into it. Thanks again.